Okay, you can start the session. Have a good session.
Okay. Welcome to quantum cryptography session, 2 session. We will have 4 talks, and we will have a question time after each talk. So the first talk is new approaches for quantum copy protection by Scott Aronson, Jeffrey Liu, Chi-Pen Liu, Mark Jandari, Yuji Zhang. Jeffrey will give a talk.
Okay, so can you guys see the slides?
Yeah.
Okay, I'm going to talk about, hello, I'm Jiahui. I'm going to talk about new approaches for quantum copy protection. This is joint work with Scott Aronson, Chi-Pen Liu, Mark Jandari, and Yuji Zhang. As we know, quantum no cloning principle does not allow us to copy an arbitrary quantum state. And this property has been applied in quantum cryptography. One famous example is quantum money. A quantum money state encodes a money value and a serial number. A valid money state can get verified by the bank, but the user with 1 copy of money state cannot produce 2 copies that both pass verification. And we want to go beyond quantum money to encode more complicated classical information into unclonable quantum information. So Aronson in 2009 put forward quantum copy protection. A copy protection algorithm would turn a classical function f into a quantum state. This state can still be used to run on any input so that you get the same evaluation as the original underlying classical functionality. But the polytime adversary cannot turn this state into 2 copies that both compute the function f correctly. Aronson, in his work, also gave the first copy protection construction for any unlearnable functions using a quantum oracle. So what's unlearnable function? An unlearnable family of functions is a family of functions that cannot be learned through its input-output behavior by a polytime adversary, and here specifically a quantum polytime adversary. It's clear if a function is learnable, it can never be copy protected because the adversary can just recover the functionality from the program by learning it. Therefore, we only care about copy protecting unlearnable functions. But one drawback of Aronson's scheme that it uses a quantum oracle. Quantum oracles implement functionalities of quantum circuits, while classical oracles, of course, only implement classical circuits. Both oracles can be seen as a virtual black box obfuscation for the underlying circuits, but obfuscation for quantum circuits is yet a stronger assumption than the classical one. Therefore, Aronson 2009 asked if we can build copy protection using only classical oracle. We answer this question with a yes in our results. Our main result can be divided into 3 parts. Before going to the construction, we briefly go through some improvement on the security definition. As we mentioned before, the adversary, in order to succeed in attack, needs to produce 2 Pyro copies that compute the function correctly. But how do we test if a Pyro program compute function correctly? Well, given only 1 copy of each Pyro program, then we may run into issues like the Pyro programs cannot be run for multiple times. They can be entangled. They may be only partially correct. Despite these issues, they may still be meaningful Pyro programs that are good to use for some freeloaders, and we need to find out about these attacks. Therefore, we give a physically meaningful way to test Pyro programs efficiently when facing these problems. Next, we give a construction to copy protect unlearnable functions using a classical oracle. We are inspired by the hidden subspace idea from Aronson Cristiano, 2012, public key quantum money scheme. A hidden subspace A is a secret subspace chosen randomly by the challenger. It has exponentially many elements in it, but it's still exponentially small compared to the full space. And the subspace state cat A is an equal superposition of all elements in A. Substates have the following properties. If we do QFT to the state, we get its dual subspace state with superposition of vectors in A perp. Moreover, we need the following hard problem. When we give a quantum adversary 1 copy of state A, and access to membership oracles for A and A perp, which check if the input vector is in the corresponding subspace. Such a quantum adversary bounded polynomially in queries cannot produce two non-zero vectors, one in A and one in A perp. And our security will rely on this provably hard problem. Our copy protection construction for F consists of one copy of state A and two oracles. Each oracle checks if a part of the input is in A or A perp, respectively, and then gives a secret share of the function F evaluated on X. Combining the output of these two oracles, a user can recover correct evaluation of Fx. To prove security, we say if a quantum polynomial type adversary is able to produce two programs when given only one copy that compute F correctly, we can violate the hard problem that we just mentioned, or violate the unlearnability of F. Adversary may cheat by making the programs entangled, but through our careful analysis, we can see even for entangled programs, the above reduction still goes through. After we have an oracle construction, we wonder if we can move to a construction using more practical crypto assumptions. However, unfortunately, we have a barrier if we want to remove oracles. A concurrent work shows that using post-quantum harness of learning with arrows and quantum fully homomorphic encryption, we can build a circuit that is unlearnable, but can never be copy protected by using some non-black box techniques. So in the face of this barrier, the next achievable directions are, first, consider weakening security notions. There are possibly weaker but meaningful security notions for quantum copy protection, where we can do better. And the second direction is we don't relax the security, but we only copy protect specific classes of functions like point functions or PRFs. We will only focus on the first direction here. We put forward a new notion called copy detection. Using this notion, we build copy detection scheme for any watermarkable functionalities, combined with the security of public key quantum money. And watermarkable functions include a lot of cryptographic functions, such as PRFs, public key encryptions, and signatures. Thank you. That's it for the 5-minute talk, and please refer to our paper or the long talk for more details.
Thank you, Jeffrey. If you have a question, please type at the chat or Zurich chat. So there is no question. So if you have a question, we will have a discussion time after the last talk. So please, if you want to ask a question, please type at Zurich chat or Zoom chat. Okay, so let's move to the second talk. The second talk is Hidden Concept and Application to Unclonable Cryptography by Andrea Coladangelo, Jeffrey Liu, Jipan Liu, Mark Chandleri. Jipan will give a talk.
Okay, thanks for the introduction. Can you see my slide?
Yeah.
Okay, so yeah, let's start. So my name is Jipan Liu from Princeton University. I'll be talking about this talk, hidden cosets and applications to unclonable cryptography. This is a joint work with Andrea Coladangelo, Jeffrey Liu, and Mark Chandleri. So the no cloning principle or theorem of quantum mechanics say that quantum information cannot be generally copied, and it opens the door to many classically impossible cryptographic primitives. This example include quantum key distribution by Bennett and Broussard, quantum mining, which was first studied by Wisner, quantum copy protection, first by Arison, using quantum random oracle, and recently from the last talk, using classical oracles. There are many applications like signature token, unclonable encryption, and decryption. And this application relies on some forms of no cloning theorems of particular quantum states. And most of these applications are based on BB84 states or Wisner states, which is first used by Wisner, and subspace states first used by Arison and Cristiano. And in this work, we propose a new notion that is an analog of both the BB84 states and subspace states, which we call coset states. We show in this work that coset states possess all important properties of BB84 states and subspace states. We will further show that because coset states have more algebraic structures, they improve many of these applications. So we look at these applications from subspace states. Briefly speaking, so for a quantum signature token, is a quantum token allows the user to sign an arbitrary single message, but cannot sign two different messages. And an unclonable decryption scheme is an encryption scheme where the decryption key itself is an unclonable quantum key. So previous results show that signature token and unclonable decryption exist relative to classical oracles. In other words, they assume post-quantum secure virtual black box obfuscation for classical circuits. And in this work, we show that this generalized notation called coset states also gives this application, but in the plane model, by assuming post-quantum I/O and a one-way function. For unclonable decryption and copy protection of PRFs, we need to additionally conjecture that the coset states have a stronger property. The property is proved by Koff and Vidic in a follow-up work. So now let's introduce coset states. A coset states for a subspace A and two vectors, S and S prime, is a quantum state that satisfies the following property. If you measure the state directly or in the computational basis, you will get a uniformly random vector in the coset A plus S, which is the set of the vector in A, but shifted by S. If you apply Hadamard on the state and then measure, you will get a uniformly random vector in the coset A perp plus S prime. And similarly, for the subspace states, it encodes the subspace and the dual subspace in the computational basis and the Hadamard basis. This is already introduced in the last talk. They do not have the hidden shift S and S prime. So coset states satisfy the direct product hardness property. It says that for a query-bounded quantum algorithm, given a single copy of the coset states, even if it gets oracle access to both membership checking oracle, that is the oracle for checking if a vector is in the coset, it cannot find two vectors in both cosets. And for subspace states, it's similar. That is, you cannot having a single copy of the subspace states and two membership checking oracle and output two non-trivial vectors in both subspace. So the direct product hardness of coset states naturally gives a construction of signature tokens, but due to time restriction, I'm not going to talk about it here, but the construction is still relative to classical oracles. It's especially because the membership checking oracle here will be used as a verification key for signature schemes. So therefore, as we see in the previous discussion, the verification key is a VBB obfuscation. So to achieve the construction in the plane model, the one natural attempt is to replace VBB obfuscation with I/O. The similar idea was deployed to achieve quantum money in the plane model, where they rely on a weaker property than direct product hardness. So Landry shows that this idea works in the plane model by instantiating the obfuscation with I/O. And one can try to apply the same idea on direct product hardness property for subspace states. But however, in the same reduction, one will run into a technical problem, and thus the reduction fails. In this work, we show that with coset states, we can instantiate obfuscation with I/O and still preserve the computational hardness in the plane model. And therefore, let's conclude the first part of the work. That is, we show coset states satisfy computational direct product hardness, assuming post-quantum I/O and a one-way function. And it naturally gives signature token schemes in the plane model. And this is a picture of the work. We also show that coset states have other properties and thus give different applications. And note that although we achieve different primitives in the plane model, the application above the yellow line or below the yellow line, they require completely different structures of coset states. Therefore, we think they are conceptually different ideas and works. And for more details, please refer to the full paper and the longer talk video. And that's it. Thank you.
Thank you, Chi-Peng. If you have a question about Japan's talk, please type on Zoom chat or Zurich chat. Yeah, I didn't find a question to Japan, so let's move to the third talk. Okay, the third talk is on tight quantum security of HMAC and NMAC in the quantum random oracle model by Akinori Hoseyamada and Tetsu Iwata. Akinori will give a talk. You are muted, Akinori.
Thank you. Can you hear me and can you see my slide?
Yes.
Thank you. Thank you for introduction. This is a talk on tight quantum security of HMAC and NMAC in the quantum random oracle model. This is joint work with my supervisor, Tetsu Iwata. HMAC or hash-based MAC looks like this. It is the most basic approach to convert Markov-Danglard hash functions into MACs. And it is standardized in FIPS and used in many applications. So this construction is very important in symmetric key cryptography. And essentially, this construction is a single key construction because first, master key K is chosen uniformly at random. And then the two keys K in and K out are computed like this. And for each message, the Markov-Danglard hash function is called or evaluated twice like this. This is HMAC. And the NMAC is like this. So it is a two-key variant of HMAC. And in this construction, two keys K1 and K2 are independently and randomly chosen and used like this. So these functions, HMAC and NMAC, are proposed by Berare et al. And in the classical setting, the security of HMAC and NMAC is well studied. And it is proven to be secure against classical queries up to 2 to the power n over 2 classical queries. And so in the quantum setting, Son and Young proved that HMAC and NMAC is also indistinguishable from a random function up to order 2 to the power n over 5 or 2 to the power n over 8 quantum queries. And so this is the proven lower bound for HMAC and NMAC in the quantum setting. On the other hand, for the upper bound, there exists a trivial attack that distinguishes HMAC and NMAC from a random function by making 2 to the power n over 3 quantum queries. However, there still exists a gap between the proven lower quantum bound and the trivial upper bound. And in symmetric cryptography, it is very important to study the tight security bound for each scheme. So the natural question is, can we show the tight quantum security bound of HMAC and NMAC? This is the starting point of our research. And we showed these results. So we showed the tight quantum security bound of HMAC and NMAC in the quantum random oracle model, where the compression function H is a quantum random oracle. And we showed that HMAC and NMAC are indistinguishable from a random function against the quantum query attacks, as long as this inequality holds. And here, roughly speaking, this is the total number of quantum queries. And this L is the maximum message length. And so, roughly speaking, this bound is tight when L is not exponentially large. I mean, the tight quantum security bound of HMAC and NMAC is 2 to the power n over 3. And to prove this tight quantum security bound, we use the compressed oracle technique. And in our proof, the hardest part is to prove the probability of a bad event is very low. And to show this hardest part, we introduce a new idea to capture the uncertainty of outputs of a random function that the adversary cannot observe. This is our results. And this is a quick technical overview. So in our proof, to show indistinguishability of certain quantum oracles, we consider a bad event hit. And in our proof, what we have to prove is this probability is very small. And this event is the event that an adversary succeeds to guess an output of a random function. And here, the setting is something like this. So the adversary can observe the outputs of this composition function. And here, H is the quantum random oracle or the compression function. The adversary can observe the output of this function, but cannot observe the outputs of RF directly. And here, the randomness of RF cannot be directly used to upper bound the probability. Because this bad event hit happens only when the adversary outputs some value, and we do not know what values adversary will query. And so how to tightly bound this probability is not trivial in the quantum setting. And to upper bound this probability, we use this idea. So even after observing the output of this composition function, the value of the output of this RF has some uncertainty. So there exist lots of databases of the compressed oracle for this random function that seem completely equally likely to the adversary. And based on this idea, we observed that the problem of tightly bounding this probability can be reduced to counting arguments. This is a quick technical overview. And again, this is our results. That's all. Thank you for your attention.
Thank you, Akinori. If you have a question to the talk, please type on the chat or Zoom chat. But I don't see a question on chat. Okay, you can ask a question after talk. So let's move to the last talk of this session. The last one is quantum collision attacks on reduced SHA-256 and SHA-512 by Akinori Hosoyamada and Yu Sasaki. Akinori will give a talk.
Thank you for introduction. Hello, again. I'm Akinori Hosoyamada. And this paper is on quantum collision attacks, quantum dedicated collision attacks on reduced SHA-256 and SHA-512. This is a joint work with my colleague, Yu Sasaki. So this is our results. In this paper, we showed the first dedicated quantum collision attacks on SHA-2. More concretely, we showed a 38-step attack on SHA-256 and 39-step attack on SHA-512. And in the classical setting, collision attacks reach 31-step for SHA-256 and 27-step for SHA-512. And so we extended the number of attack runs by 7 and 12 in the quantum setting. However, I'd like to remark that these number of steps are still far from full steps because the number of full steps are 64 and 80 respectively. And the attack idea is, roughly speaking, like this. So in the quantum setting, we convert classical semi-free start collisions on these functions into collisions in the quantum setting. And our attacks are valid in the setting of time-space trade-off, but invalid in other quantum settings. And so in the quantum setting, we can consider 3 attack settings depending on available computational resources. I cannot explain details, but in this paper, we focus on this setting. In this setting, the efficiency of a quantum algorithm is measured by its time-space trade-off, and we assume that there is no quantum RAM available. And we also assume that there is a quantum computer of size S and classical computer of size S. And in this setting, the current best generic quantum collision finding algorithm is the parallel law method. And this gives the trade-off T is equal to 2 to the power n over 2 over S, as observed by Bernstein. And in this setting, we focus on this setting. And next, I'd like to talk about collision and semi-free start collision. When we talk about a collision of Markov-Dangaard hash function, we assume that there exist 2 distinct messages that yield the same output value. And we also assume that the IV initial values are equal. and the IV is equal to the original specified constant. And then next, when we talk about semi-free start collisions, we assume that again, we have distinct messages that is the same output. And we also assume that the IV value is the same. But this here, the important point is the IV is not necessarily equal to the original specified value. So this is the difference between collision and semi-free start collision. And next, I'd like to talk about important previous classical work on SHA-256. So Mendel et al. Showed a 31-step collision attack and 38-step semi-free start collision attack on SHA-256. And the important point is the 31-step collision attack. This attack is mounted by converting 31-step semi-free start collisions into a 2-block collision. And so a 2-block collision looks like this. This is the first block, and this is the second block. And very roughly speaking, if we can make many semi-free start collisions for 2 to the power x choices of IVs for the second block, then we can find a 2-block collision in type 2 to the power n minus x in the classical setting. And this attack is considered to be a valid collision attack in the classical setting, only if its time complexity, this one, is less than the generic birthday bound. And this inequality is equivalent to this condition. And so this condition can be regarded as a validity condition for the number of IVs in the semi-free start collision attacks to be converted into a collision attack in the classical setting. And the important point is the 38-step semi-free start collision attack is not converted into a collision attack in the classical setting because this condition is not satisfied for 38-step attack. And in the quantum setting, our idea is this condition can be relaxed in the quantum setting. And roughly speaking, we observe that this condition becomes x is greater than 0 in the quantum setting. So the condition is much relaxed in the quantum setting. And based on this observation, we actually found 2 valid dedicated quantum collision attacks on SHA-2. So we converted 38-step semi-free start collision attack on SHA-256 by Mendel et al. And 39-step semi-free start collision attack on SHA-512 by O'Brien et al. Into a 2-block collision. And with some analysis and computer experiments, we confirmed that these attacks are indeed valid in the quantum setting. And the complexity becomes like this. So that's all. Thank you for your attention.
Thank you, Akinori. Okay, the time for question. So first, if you have a question to Akinori, you can ask at Zurich chat or Zoom chat. Okay, so let's move to the discussion session. First, there is one question to Jeffrey. Can you explain the differences between copy detection and the software releasing? And how is your security definition of copy production compared to other definitions? For example, the one given in the work by Pradangelo, Magents, and Porembra.
Okay, so the question is compare the definition to CMP20 and also asked about secure software leasing, right?
Yeah.
Okay, so I just say the main first I'll talk about the difference with SSL. So I just say the main difference is that copy detection emphasizes the public detectability of the scheme. So anyone with a public key can detect if a program is pirated, even without knowledge of the functionality. This is guaranteed by the security of public key quantum money and public extractable watermarking. Secure software leasing is not necessarily public verifiable, but you can make it if you construct the scheme. Like especially for the infinite term, you can construct in a way that is public verifiable. But in the asymmetric version, the finite term SSL, so we check if one side of the pirate program is exactly the original program and run and test the other program. Which is like similar to copy detection. But especially in the first check, it can only be done by the vendor, not any users. Also, another minor difference is that SSL checks the Pyro program's performance in a worst case flavor. They had to compute the functionality correctly on all inputs. Ours only checks the average case by sampling inputs from a distribution associated with the function. And to compare with copy protection definition in CMP20, I think their definition should be the same as Ericsson 2009. So they do not worry about the problem of like whether we are given only one copy of Pyro program in each security game, and they may not run for many times. The problem with estimating the success probability, because I think the success probability is calculated, is estimated over invoking several security games. So of course this is a correct and makes sense security notion. I'd say the first step is our definition. Of course, we only just run one game. It would imply theirs, like depending on like the parameters you set for like a successful probability for the adversary. And the second thing is like ours is like meaningful, more physically meaningful, because in classical security games, when the adversary is classical, you can always say I can invoke security game several times because I can rewind the adversary, can reset it. But quantum case is not necessarily true. So this is maybe a little subtle, and so we want to, and this is also more reduction friendly. If we just invoke the security game once and estimate the success probability efficiently, so that would like help our reduction to go through. So both in this paper, this new approaches paper, and the paper hidden cosets, we would deploy the advantage of this definition, because actually the testing procedure is a measurement procedure that would help us the reduction to go through when we face quantum adversaries. So does that answer your question?
Yeah, I think so. Thanks.
Thank you. Okay.
Okay, Chris is raising a hand. Chris, please.
Yes, a question about the quantum random oracle for NMAC and HMAC paper. There's a term of L to the 3/5. I think L was the message length. Is that right? I was just wondering what the effect of that is on the on the concrete bounds, and what the prospects might be for removing or reducing that term. That would yield an even tighter bound, if I understand right.
Okay, thank you for question. So ESL is the length of the messages, and I'm sorry, could you please say your first question again?
Yeah, I guess the implications for that is if you have a very long message, the bound is not as useful or not as tight. And so what do you think are the prospects for reducing that term? Is it a proof artifact, or is it something more inherent that you think?
Actually, I think the bound can be more tight about the message length. But currently, I do not have any idea about how to do that. Actually, our proof is somewhat rough in some sense, because so we consider many transition of games, and so for example, we consider games G1, G2, G3, G4, and something like that. And for each transition from GI to GI plus, I consider that the proof for this transition is tight for each transition. But I don't know. Well, maybe I think the way of choosing such games is not good, and I think the bound can be made much better. But currently, I don't know how to do it.
Okay, thank you.
Thanks.
Thank you.
Prabhanjan is raising a hand. Please ask a question.
Yeah, this question is for Shipeng. Is there some barrier to achieving computational direct product hardness for subspace states? Or is it just because the instantiation from IO somehow fails?
Okay, so basically, I would say so it's not like a specific problem. It's more like when you do the reduction, you will end up with a specific game if you follow the technique in Mark's paper, like the subspace hiding obfuscation, in which you replace a unknown subspace with like a slightly larger random subspace. And if you follow that idea, you will end up with a problem which is actually easy. So without this shift, you will reduce the problem to a very easy problem. So I'm not sure if that's the problem of the subspace state, or that's just like a problem of doing reductions. So, but to me, there's like no reason to say maybe there's problem of subspace states. For now, I just believe it's more like a technical problem.
And there's also problem with the reduction. For all we know, the candidate could still be secure with a different proof technique.
For now, I would say that, yeah. Yes.
Thanks. I also have a question to Chipen. You achieved copy protection for only for PRF. Could you extend your technique to achieve copy protection for decryption function or a signature function?
For decryption, it is, so we call it like unclonable decryption. So it's basically a copy protection of decryption circuit. So, but for signature, I think we don't think about that, because signature token is not like a copy protection of signature, right? It's more like a one-time signature, but you cannot produce two signatures using just a single quantum token. So I haven't think about that, but probably it can be constructed from the copy protection of PRFs, maybe in a black box way. I'm not 100% sure, but that's a good question to think about.
Okay, thanks.
Yeah.
There is one question in Zurich chat. I think this question to Akinori. I'm not sure I understand what is meant by the setting. Is that a way of saying that the attack requires quantum RAM to run, or does it mean something else?
Okay, thank you for the question. I'd like to provide an answer, and I'd like to share again my screen. Can I share the screen again to explain it?
Yeah, sure.
So I think your question is on the setting, and so as I mentioned before, we are in this setting, and so so first, the most basic and the most basic setting is we assume that there is one quantum computer and there is large quantum RAM available. In this setting, it is widely known that the best collision finding generic algorithm is the BHT algorithm, and it finds a collision of a random function in time 2 to the power n over 3. But it also requires a large quantum RAM of 2 to the power n over 3. And in the quantum setting, if such a large quantum RAM is available or not is unclear. And so suppose we do not we regard the qubit for computation and the qubit for the memory are same or equal or equivalent. And suppose again that the efficiency of an algorithm is measured by its time-space trade-off, like this. And then, as observed by Bernstein, we can see that in this setting, I mean the setting of time-space trade-off, we can say that the best generic algorithm is the parallel law method. And so that is the explanation for the settings. And my answer is we just consider that some other conditions that does not require any quantum RAM, and our attack do not require any quantum RAM or something like that. And so yeah, that's what I can say now. And for more details about the settings of quantum attacks, please read our paper at Eurocrypt 2020, because we explained more about those settings on that paper. Thank you.
Thanks. Okay, so we are running out of time, and there is no more question on chat. Okay, thank you so much for all speakers of this session. If you have more